You know that moment. You're scrolling through an old inbox trying to find um, a specific email or maybe hunting for a product on some e-commerce site. When that search snaps back instantly, it feels almost like magic. But when it lags, even for a few seconds, it's pretty frustrating, right? Today, we're sort of pulling back the curtain on the technology that powers that speed, or sometimes, yeah, bogs it down, database indexing. Our mission in this deep dive is really to quickly get you well-versed in what database indexing is, why it's absolutely critical for application performance, the common missteps to avoid, and some advanced techniques. We're doing this by sifting through a stack of articles and discussions we've gathered.
It's absolutely true. The performance of an application often hinges on, well, how well its database indexing is implemented. Done correctly, it can drastically improve query speeds and, reduce the load on your servers. That keeps users happy and systems stable. But miss the mark, and you're looking at painfully slow queries, bloated storage, maybe even system crashes when traffic spikes. This isn't just some technical detail, it's really a cornerstone of robust system design.
Okay, let's unpack this, maybe with a simple image. Imagine your database isn't this complex piece of software, but a colossal library. Millions of books, right? Each book representing a row of data. Now, if you wanted to find a specific title, I don't know, The Great Gatsby, but there was no card catalog, no genre sections, just this endless labyrinth of unorganized shelves, what would you do?
You'd have to look at every single book.
Exactly. Pick up every single book one by one until you found it. That painstaking process. In database terms, that's a full table scan.
Yeah, precisely. And that works fine if you have like a personal bookshelf with a few dozen books. But scale that up to a library with millions of volumes, and that full table scan becomes utterly impractical. Queries take ages. This is exactly what indexes are designed to prevent. They provide a highly structured map, right? Fundamentally changing how the database accesses data. Instead of sifting through every piece of information, an index tells the database precisely where to go. It minimizes those costly disk reads and gets you to your data in a flash. For anyone designing systems, from mid-level engineers to seasoned architects, understanding this basic principle and its implications is really non-negotiable.
Right. So if indexes are RMAP, what kind of internal structure makes them so efficient? The workhorse, I think, for most database indexes is a data structure known as a B tree, or maybe its slightly more specialized cousins, the B plus tree. They sound a bit intimidating, maybe, but they're quite elegant in their simplicity. Picture a B tree not like a traditional tree with branches pointing up, but more like a balanced, deep root system. It's a self-balancing structure that keeps data or keys in assorted order across various nodes. You have the root, internal nodes, and leaf nodes. Each node can hold multiple keys and pointers to its children, ensuring that you can navigate to any piece of data incredibly quickly. You typically only touch a few nodes, regardless of how massive your dataset actually is.
Yeah, and what's fascinating here is how B+trees optimize this whole concept specifically for database performance. The core difference, really, is that in a B+tree, all the actual data, your full table rows, resides only in the leaf nodes. Those are at the very bottom of the tree. The internal nodes, the ones higher up, they only store keys and pointers. They act purely as a rapid navigational guide. This structure allows each internal node to point to many more children, which keeps the tree shallower and therefore lookups faster. Fewer disk accesses.
Fewer disk accesses. Okay,
Yeah.
that makes sense.
Exactly. Plus, those leaf nodes are usually chained together, often in a doubly linked list, which is brilliant for quickly scanning through a range of data, like finding all transactions between two specific dates. MySQL's InnoDB storage engine, for example, relies heavily on B+trees. It stores all your table data in a B+tree, using your primary key as the tree's key. PostgreSQL also uses B-trees extensively for primary keys and most other indexes too. Even secondary indexes, those are the indexes on non-primary key columns. They're often B+trees themselves. But instead of holding the full data row, their leaf nodes typically just store the primary key of the row, which usually leads to a quick two-step lookup.
Okay, that connection between B trees and how data is actually stored seems pretty fundamental. But then there's this even deeper layer, isn't there, when we think about how we design our primary keys? Can you maybe elaborate on why that choice is so pivotal?
Oh, absolutely. The type of primary key you choose has a huge impact, a profound impact, really. Imagine you're inserting new data into that B+ tree we talked about. If you use something like a random UEI DV4 as your primary key, new insertions are well, unpredictable. They're like throwing darts at random points across the entire B+ tree structure. This often forces the database to touch many different data pages on disk and frequently reorganize the tree to keep it sorted. That means lots of disk reads and writes.
Right, fragmentation, basically.
Exactly. It can create significant performance bottlenecks, especially under heavy write loads. But if you use a sequential integer, like an auto-increment vigint, new data almost always goes to the rightmost path of the tree. This means insertions tend to reuse existing data pages and keep newly added information physically close together on disk. This append-only pattern is incredibly efficient, not just for writes, but also for subsequent reads that often access recent data. And another subtle point, smaller primary keys, like an 8-byte vigint compared to a 16-byte UEVID, allow more keys to fit within each node, which naturally results in a shallower tree and inherently faster lookups overall. It's a really crucial design decision.
Okay, so it definitely sounds like indexes are incredibly powerful. We want fast searches and these structures deliver. But like almost everything else in technology, they can't be a magic bullet, can they? There has to be a trade-off somewhere. What's the catch?
That's precisely the indexing paradox. You're right. Indexes aren't free. Think of them as maintaining an entirely separate, sorted copy of part of your data. This means they require additional disk space, sometimes nearly as much as the original table data itself. That's one cost. But maybe more critically, every write operation, an insert, update, or delete, doesn't just need to modify the main table. It also has to update every single index on that table to keep them consistent.
Ah, the right penalty.
Exactly. This overhead can significantly degrade write performance. For instance, B-tree indexes need to be rebalanced sometimes. And updating a primary key in a clustered index, like an InnoDB, can be particularly expensive because it might force a complete reorganization of where that data row is physically stored on disk. I actually saw a logging table once designed to capture really high-volume event data, absolutely crippled by too many indexes. They were inserting millions of records an hour, but rarely querying the old ones. The database literally spent more time updating indexes than actually writing the new data. And for small tables, with only a few hundred rows, the cost of maintaining an index often outweighs any benefit you'd get from a simple sequential scan anyway. So yeah, it's always a delicate balance.
Okay, so it's clear indexes aren't just a set it and forget it kind of solution. Given these trade-offs, how do we practically apply this knowledge? How do we avoid the pitfalls and make sure we're truly optimizing performance?
That really is the million-dollar question, and frankly, a common stumbling block. Many of the issues I've seen in systems and what articles like 10 common mistakes in database indexing often point out boil down to a few key errors. First, the most obvious one, not having any indexes at all. That's your full table scan nightmare we talked about.
The default slow mode.
Pretty much the fix. Use tools like Explain to identify your slowest queries. Then add indexes to the columns frequently used in where clauses, join conditions, and order by statements. Be strategic about it.
Okay, so identify the bottlenecks, then apply the fix where it matters.
Yeah.
Makes sense.
Exactly. But then on the other end of the spectrum, using too many indexes or just indexing every single column is another common trap. Each index, like we just discussed, consumes storage and definitely slows down writes. You have to be judicious. Regularly review and maybe remove indexes that aren't actually being used. Tools like pre-status or nexes and PostgreSQL can help you spot these. Another crucial mistake is ignoring composite indexes or using the wrong column order in them. If your queries often filter by multiple columns, say userid and status, a single column index on just userid isn't going to be super helpful for the whole query. A composite index like userid status is usually far more efficient. And remember, these composite indexes generally work left to right, so you want to put your most selective column or the one you filter on most often first in the index definition.
The order matters. Got it.
Absolutely. Also, forgetting foreign keys is a huge oversight. Foreign key columns almost always need an index. Why? Because they're heavily involved in JOI operations. And without an index, deleting parent rows can cause really serious lock contention on the entire child table. It can grind things to a halt. So, general rule, always index your foreign key columns. And finally, maybe the most important one, not testing index performance. It's like driving blind. Don't just assume an index will magically fix everything. Use Exaplain or similar tools to verify that your database is actually using your new index and that it's helping and not hurting. Sometimes, a poorly designed query is the real problem, not the lack of an index. Optimize your queries first. And for data that's read very frequently but changes rarely, maybe caching is a better solution than adding yet another index.
Wow, okay. These aren't just like theoretical suggestions. These sound like real-world performance multipliers or potential killers if you ignore them. It really underscores that informed, strategic choices are absolutely paramount. This is how you move from just knowing what an index is to truly understanding how to wield this power effectively. Now, shifting gears a bit, when you type a query into Google or maybe search for articles on a blog, you're usually not hitting a traditional B tree for that primary search, right? For full-text searches, there's this fascinatingly different data structure at play, the inverted index. Instead of each document listing its words, which you could call a forward index, an inverted index works in reverse. It maps each unique word to a list of all the documents it appears in. So you query a word, and bang, it immediately tells you all the places it lives. It's really the backbone of pretty much every search engine out there.
That inverted nature is precisely why it's so incredibly fast for search. The process, as you'd find in articles digging into this, usually starts with pre-processing the text. Things like removing common stop words, words like the or a or is, then maybe stemming words down to their root forms, normalizing case, that sort of thing. Then the text is broken down into individual terms or tokens. And for each unique token, this inverted list is built containing the unique IDs of every document where that specific term appears. So when you submit a query like database indexing, the system quickly looks up database and indexing in these pre-built lists. It retrieves the matching document IDs, often intersects those lists to find documents containing both, and then ranks them by relevance. And these inverted lists can be incredibly detailed. They might even include information like the word count within each document or the specific positions of words. That position data becomes vital for things like proximity searches, finding the exact phrase tropical fish, or maybe even tropical within 5 words of fish.
Okay, that makes sense for, say, a blog's search function. But imagine a system like Google, indexing billions and billions of web pages. Those inverted lists for common words like the or and must be astronomically long. How do you possibly keep these massive inverted indexes fast and manageable at that kind of scale?
Yeah, that's where the really clever engineering comes in. Advanced optimizations and compression become absolutely critical. For fast query processing, particularly with conjunctive queries where multiple terms must be present, like fast database index, search engines employ techniques like skip pointers within those long inverted lists. These pointers allow the search algorithm to essentially jump over large blocks of documents that are guaranteed not to contain all the required query terms. This dramatically speeds up the process of finding the intersection of those lists.
So it skips chunks it knows won't match anyway.
Precisely. And for top K queries where you only need, say, the 10 most relevant results, not all possible results there are advanced algorithms, things like WAND or Block Max WAND, BMW. They use what's called safe earlier termination. They dynamically calculate relevance thresholds as they scan the lists. This lets them skip processing documents or even entire blocks of documents within the index that simply cannot possibly make it into the top K results based on scores calculated so far. This hugely reduces computation, and it's particularly effective for shorter, common queries. Now, the other massive challenge is just the sheer size of the index. Inverted lists can indeed be enormous, especially for very common words. There's even a linguistic pattern called Zipf's law, which basically says a few terms are incredibly frequent while most are very rare. This heavily influences index size. So to manage this, compression is absolutely essential. The key insight here isn't necessarily to memorize every single compression algorithm, but to understand that for massive scale search, engineers use incredibly clever math and hardware-aware techniques. Simple techniques like delta encoding are very effective. Instead of storing the full document IDs, like 101, 1005, 1012, you store the differences, 1001, then plus 4, then plus 7. Since the lists are ordered, these differences, or deltas, are usually small numbers and can be stored very compactly. Beyond that, you get into sophisticated codes broadly categorized as bit-aligned, like Elias codes, and byte-aligned, like vbyte simple 9. The latest advancements even leverage modern CPU instructions, things like SIMD, in techniques like SIMD BP128. These pack and process batches of these compressed numbers incredibly fast, offering an excellent trade-off between index size and query speed. Knowing this stuff exists helps you understand what technologies like Elasticsearch or Solr are actually doing under the hood to make search fast at scale.
That's a seriously deep dive into search. Wow. Okay, but what about when your data isn't just text or numbers, but actual geographical locations? How do databases handle queries like find all restaurants within 5 miles, or maybe what buildings intersect with this planned road construction zone?
Right, geospatial data. It's inherently multidimensional. You have latitude and longitude at least. And traditional single-dimension indexing methods like our B+trees just aren't well suited for it. They don't handle 2D or 3D space efficiently. Queries involving spatial calculations like distance, overlap, containment can become excruciatingly slow without specialized indexing. There are discussions online highlighting challenges people face with MySQL's geospatial features, if not indexed properly. The solution lies in geospatial indexing. This involves creating specialized data structures designed for multidimensional data. Common algorithms you might hear about are R-trees and quad-trees. At a high level, these indexes work by organizing space. They divide the geographical area hierarchically into bounding boxes or grid cells. This allows the database to very quickly narrow down the search to only the relevant geographical areas for a given query, filtering out most of the data immediately. The benefits are dramatically improved query response times, better scalability as your location data grows, and optimized resource usage. Databases like MySQL provide special spatial data types point, line string, polygon, and specific functions. Things like st-distance sphere to calculate distances accurately on a sphere, st-intersects to check for any overlap, and st-contains to see if one shape is entirely inside another. When you combine these powerful functions with appropriate spatial indexes, analyzing complex spatial relationships becomes incredibly efficient.
Okay, so after covering all this ground B trees, primary keys, right costs, inverted indexes, geospatial stuff, why should you, the listener, really care about these nuances? The specifics of composite index orders or the intricacies of inverted index compression. What's the real-world impact here?
This is absolutely where theory meets practice, especially when you get into system design interviews or real-world architecture. As one experienced interviewer pointed out on Reddit, just saying something like, "Oh, I'll use MongoDB for storage," is what it's considered a pretty junior level answer. A senior engineer is expected to go much deeper. Okay, why MongoDB specifically? Why choose NoSQL over a relational database for this particular system? How does the CAPI theorem influence your choice here? What scale are we talking about for the database? How will we handle sharding, replication? And crucially, how will this design handle, say, 1 million queries per second? Understanding indexing isn't just about tweaking a database setting after the fact. It's fundamental to designing resilient, scalable, and high-performing systems right from the very foundation. It's about knowing the trade-offs, making informed choices between different database technologies or index types, and being able to confidently justify those architectural decisions. That's what separates levels of engineering expertise.
What an incredible deep dive, seriously. We've journeyed from the absolute basics of how indexes prevent those painful full table scans, right to the elegant architecture of B trees and B+trees. We carefully balanced the trade-offs between read speed and write performance, and then explored the really sophisticated worlds of inverted indexes for search and specialized geospatial indexing. It's abundantly clear, I think, that database indexing is a powerful, indispensable tool, but definitely not a magic fix. It really demands careful thought, strategic implementation, and probably continuous monitoring to truly unlock its potential.
Absolutely. And maybe this raises an important question for all of us to think about. In a world that's just drowning in ever-growing amounts of data, where application performance often directly translates to user satisfaction and, frankly, business success, how much more untapped potential, how much more speed is truly hiding there in plain sight within our systems, simply waiting for us to choose the right index, applied in the right place, configured at the right time. It's a continuous journey, really, of learning and experimentation that every system designer, every developer constantly faces.